In this video, we will explore the fascinating world of operating systems and the different types that power our digital devices. We'll examine various operating system architectures and their real-world applications. Get ready to dive in and discover the core functions that make our computers, smartphones, and other gadgets work seamlessly. Let's start with batch operating systems. These systems group similar jobs together into batches. Once a batch is formed, it is executed without requiring any user interaction. Imagine submitting a stack of punch cards to a mainframe computer, and it processes them one after the other without stopping for input. A key advantage of batch processing is that it minimizes the idle time between job executions, ensuring that the computer is constantly working. However, there is no user interaction during the processing, which means you cannot make changes or receive immediate feedback. Historically, batch operating systems were widely used in mainframe environments for tasks like payroll processing and large data analysis. Next up are time-sharing operating systems. These systems allow multiple users to interact with the computer simultaneously. It achieves this by rapidly switching between tasks, giving each user a small slice of time or a time slice on the central processing unit (CPU). Imagine several people working on the same computer at the same time, each feeling like they have exclusive access. The quick response times are ideal for interactive use, making it possible to edit documents, browse the web, and run applications smoothly. Time sharing is the foundation for modern multi-user systems, allowing numerous individuals to share computing resources efficiently. Now let's look at desktop operating systems. These are designed for personal computers and provide a graphical user interface, known as a GUI, that allows users to interact with applications and manage resources easily. Think of the familiar interfaces of Windows, macOS, and Linux. Desktop operating systems are characterized by their multitasking capabilities, allowing you to run multiple applications at the same time, such as a web browser, a word processor, and a music player. They also support plug-and-play devices, making it simple to connect and use peripherals like printers, cameras, and external hard drives. User account management is another key feature, allowing multiple users to securely share the same computer. Moving on to server operating systems, these are designed to manage network resources and provide services to client computers in a network environment. Unlike desktop operating systems, server operating systems prioritize high reliability and uptime, ensuring that critical services are always available. They are optimized for network services such as web hosting, email, and file storage. Enhanced security features are built in to protect sensitive data and prevent unauthorized access. Server operating systems support multiple users simultaneously, allowing many clients to access resources and services. Advanced storage management capabilities are also included to handle large volumes of data efficiently. Let's examine embedded operating systems. These are specialized operating systems designed to operate within devices with specific functions and limited resources, from smart TVs to car systems. Embedded operating systems are optimized for specific hardware, meaning they are tailored to work efficiently with the device's processor, memory, and other components. Resource requirements are minimal to ensure that the operating system can run on devices with limited processing power and memory. Many embedded operating systems offer real-time capabilities, allowing them to respond quickly and predictably to events. They also emphasize high reliability and stability, ensuring that the device operates consistently without errors. Often, embedded operating systems run on read-only memory, ROM, or flash memory, which are non-volatile storage solutions that retain data even when power is turned off. Many embedded systems have limited or no user interface, as they are designed to perform specific tasks automatically. Real-time operating systems, or RTOS, are designed to process data and events with precise timing and a high degree of reliability. Imagine an anti-lock braking system in a car, or a life support system in a hospital. Real-time operating systems are crucial in environments where timing is critical. These operating systems provide guaranteed response times, ensuring that tasks are completed within strict deadlines. They exhibit deterministic behavior, meaning that the output is predictable and consistent for a given input. Priority-based scheduling is used to ensure that the most critical tasks are executed first. Real-time operating systems minimize interrupt latency, which is the delay between an event occurring and the operating system responding to it. They have a small memory footprint and are often used in applications where failure to meet a deadline can have serious consequences. Finally, we have distributed operating systems, which manage collections of independent computers, making them appear as a single coherent system to users. These operating systems connect multiple autonomous computers, allowing them to work together to solve complex problems. Transparent resource sharing is a key feature, enabling users to access resources on any computer in the network without knowing their physical location. Distributed operating systems provide fault tolerance and redundancy, ensuring that the system continues to operate even if one or more computers fail. Scalability is another advantage, making it easy to add more computers to the system as needed. Location transparency means that users do not need to know where resources are located in order to use them. Distributed security mechanisms are implemented to protect data and prevent unauthorized access across the network. Now, let's take a look at a comparison of the different types of operating systems we've discussed. Batch operating systems have minimal user interaction, relatively low resource usage, slow response times, and limited scalability. They are typically used for tasks like payroll processing. Time-sharing operating systems offer interactive user experiences, medium resource usage, moderate response times, and decent scalability. They are suitable for multi-user systems. Desktop operating systems provide highly interactive user interfaces, medium resource usage, fast response times, and moderate scalability, making them ideal for personal computing. Server operating systems have limited user interaction, high resource usage, variable response times, and high scalability, which makes them suitable for web, database, and file servers. Embedded operating systems offer minimal or no user interface, very low resource usage, fast response times, and low scalability. They are commonly used in IoT devices and appliances. Real-time operating systems are task-specific, have medium resource usage, predictable response times, and low scalability. They are essential in medical devices and avionics. Distributed operating systems provide transparent user experiences, very high resource usage, variable response times, and extremely high scalability, making them ideal for cloud computing and clusters. Finally, let's consider the evolution and future of operating systems. In the 1950s, we saw the first generation of simple batch processing systems with minimal functionality. The 1960s brought the second generation of multiprogramming and time-sharing systems. In the 1970s, Unix was developed, introducing portable operating systems and multi-user capabilities. The 1980s marked the beginning of the personal computer operating system era with MS-DOS and early graphical user interface (GUI) systems. Windows and Linux gained prominence in the 1990s as Internet integration began. The 2000s saw the emergence of mobile operating systems and the start of cloud computing. In the 2010s, IoT operating systems, containerization, and distributed systems expanded. Looking ahead, we can expect to see AI-integrated operating systems that adapt to user behavior and optimize performance. Enhance security through hardware-based isolation and zero-trust architectures. Cloud-native operating systems that blur the line between local and remote computing. Microkernel and unikernel designs for specialized applications. Distributed operating system architectures for edge computing and IoT ecosystems. Energy-aware operating systems optimized for sustainability. Self-healing systems with autonomous maintenance capabilities. As we've seen, operating systems continue to evolve from simple resource managers to complex ecosystems that span multiple devices and computing paradigms. The boundaries between different operating system types are increasingly blurred as hybrid approaches emerge to meet diverse computing needs. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.